Hello guys, and welcome to this video where we're going to be building a RAG pipeline from scratch. Now I love RAG because that's one of the best ways to provide domain context into your LLM responses. So you take your private information, you mix it in with your prompt, you send it to the LLM, and you're able to get answers that are grounded in your private information. Now if you're still new to RAG, I have created this free cheat sheet. It's more like an engineer's pocket guide, but it can be used by project managers or anybody that is interested in RAG. And its purpose is to get you up to speed with what RAG is all about, when to use it, how to use it, and also, how it compares to something like fine-tuning and how you can also employ some optimization strategies. Now in this video, we're going to be building a simple RAG pipeline that we can just dump a bunch of documents into a folder, and it will be able to chunk those documents, embed them, and store them in a vector store, and they'll be ready for querying in your transactions with an LLM. And you can always take this project as a good base that you can improve and move into production. Now, after watching this, if you also want to see me write a version of it that can support something like an S3 bucket, feel free to leave that comment in the comment section. But enough talk, let's get started building our RAG pipeline. So in this video, we're going to be discussing how RAG works, how Retrieval-Augmented Generation works. Now, if you are still new to RAG, there is a cheat sheet in the description, so you can check the description of this video. There is a cheat sheet where you can see everything I've explained. It's free. It's a free cheat sheet, so you can just download it and get up to speed with what RAG is all about. But this video, we are discussing how RAG works and how we're going to be implementing it in the full series. So RAG has two stages. And the first is the ingestion stage. Now, the ingestion stage covers everything that has to do with taking all your private data, chunking it, embedding it, and saving it into a vector store. That's what everything in the ingestion stage is all about. So what happens here is that you take, let's say you have let's just put a square there. So you have all your information, you have all your files. Let's say we have PDF files, we have markdown files, different types of files, even web pages. So we have all these files, and the first thing we're going to do is to load them. We're going to take all these files, get all three of them, and we're going to load them into an intermediary store. So we load them into more like a data lake. So we just dump them somewhere as documents. So this is the first stage. Like I said, this is the load stage. This is what is called the load stage or the load step. So this is the load step. You load all your documents, PDF, markdown, images, media, any type of media, videos, audio stuff. You just load everything into this database. Now, once that is done, you will then need to split all these documents. You need to split all these documents because your LLM cannot, or rather your vector store is not going to take them as a whole. So if you have like a book, let's say you have a book of MySQL, we're not just going to take the whole book and embed it and put it in the vector database. We need to split it. So we're going to split it up. Let me make this the background. So we're going to split this up into different chunks. Let us represent the chunks as this. So we're going to split it up into different chunks. That are going to be of sizes that we can process and we can embed. You don't want to embed an entire book or an entire video. So we slice and dice it. And at this stage, which is called the splitting stage or the chunking stage, so you can call it anyone you like, so split or chunk, because you're actually creating small chunks of your documents. So this stage, you slice and dice your document, and you can define the size of each chunk. Another thing that you can do is that you can actually specify an overlap. For example, if you're breaking a whole document, let's say a web page, you can specify an overlap, because if one chunk stops at a point, it might be too abrupt and it might lose context. If another chunk starts from somewhere, it might not have context enough to really understand what is going on in that chunk. So you can specify an overlap and say, okay, A overlaps into B with, let's say, 500 characters, and B also overlaps into A with 500 characters, so that you can just maintain some sort of context. This is also where you want to do some optimizations, using some advanced strategies to make sure that context is not lost. But anyway, you have to chunk them. And the next stage is the stage where, just get this and duplicate it. The next stage is where we embed them. So we embed this chunks. Let me just say embed. So we embed these chunks, and we do that using an embeddings model. So you get an embeddings model. You can use one from Hugging Face, or you can use OpenAI's embedding model or Gemini's embedding model. So you take that embedding model and use it to embed these chunks and produce vectors. So here what we have is vectors. So I'm just going to just represent that with say just some values here. So we make them into vectors because this is the representation that our models understand. So we convert them, we embed them, which is the process of using an embeddings model to convert our chunks into vectors. So once we get them into vectors, we can then store them. We can then store them in a vector database. So it's our store. We'll store them in a vector database. Yeah. So these are the steps. These are the steps for the ingestion stage. The ingestion stage, like I said, the ingestion stage simply is all about taking all our raw documents and converting them into embeddings and storing them in a vector database. Let me put vector database here because that is very, very important. So you can use a vector database or a vector store. You can use Pinecone, you can use Chroma, anyone that you are most familiar with. You can even, if you are a Postgres fanboy, you can use pgvector, the pgvector extension, and just use Postgres. So you'll store them in a vector store, and this is a store that we're going to be querying in order to get context for any prompt that comes from the user, which is the next stage we're going to be talking about. The next stage is the generation stage. Generation stage. So ingest from ingest to generation. So the next phase is the generation phase, and generation phase is what you're going to be doing a lot. This ingestion phase is more like the write phase. It's more like the write phase for this whole RAG process. The generation phase is your read phase, is the read, and you're going to be doing it a lot because every single time a user asks a question, you want to query your vector store to see if you have documents that can provide context for that particular query, and then feed it into your prompt so that your LLM can have more context to work with. That's how you can get all your company information, private information, real-time data, and everything into your LLM's context. So this is generation phase. And the generation phase, what simply happens is that the user sends a query. So the user sends a query. So it's going to be user query. User query. So the user sends a query, and then we take our vector store. By the way, let me give it color. Let's say green, so that we can know that that's the guy. So we take the query, we go into our vector store. Our vector store provides something called a retriever. We're going to be saying it when we code out this entire process. So our vector store provides something called a retriever. And when we send our user query, the retriever is going to go into our vector store and is going to search for documents that match the user's query so that I can return them as context. And we can tell it how many documents we want it to return. We can say we want to return 5, we want to return 7, or we want to return 100 most relevant documents. There's actually some heuristics to understand, or rather to be able to know the maximum number of documents you should retrieve. So we get those documents, and these documents can be searched by match or semantically. It's always advised that you go semantically because that is actually the beauty of vector stores. Vectors help to define relationships between words, phrases, documents, what have you, information in general. So our retriever gets us the chunks. It gets us the chunks that relate to the user's query. So we can then take those chunks and mix it in with our prompt. So at the end of the day, you're going to have, let me get this box. At the end of the day, you're going to have a prompt that is made up of some of the embeddings retrieved, from your vector store, and the user prompt. Let's say the user asks a question such as what is tax? What is tax? So your final prompt is going to be the user's query, which is what is tax, and the embeddings that have come from your vector store. These are then mixed together and sent to the LLM. And when these are sent to the LLM now has context. This is the context, this is the query. It has context that it can use to answer you, or rather to give answers that are grounded in your private information. So it doesn't just use its knowledge base, it takes information directly from you. Let's say, for example, you're developing some internal tool to onboard new workers, and you want them to be able to ask questions about your company policies, about your bylaws, about your product and stuff like that. If you just feed that to an LLM that has no context about what your company does, doesn't have your company's private information, it will just hallucinate a lot. It will hallucinate a bunch of crap. But because you're now feeding it context from your own private documents, whenever they ask their questions about your bylaws, about your product, the LLM is going to be able to specifically answer them based on your knowledge base. One of the cool features I've seen these days is the fact that a lot of people are putting chatbots on their documentation. The LangChain documentation also has it. So people are putting chatbots on their documentation, and you can just simply query the documentation instead of searching around trying to look for answers. You can query the documentation, and it can feed off that particular. Let me get the lasso tool. It can feed off the documentation to answer your questions. You can feed off documentation to give you answers to your questions. So, and I've gotten to use that a lot. Even on the LangChain documentation, I've used that a lot. I also saw one on a site called render.com, just pretty cool. So yeah, these are one of the use cases where you can have an LLM grounded in your information and to provide value to your users using RAG. Straightforward and simple. So now that we understand the steps, we can then start building out our RAG pipeline. So in this video, we're going to begin our RAG pipeline. We're going to start building our RAG pipeline by creating the project. Yeah, this is the project setup video. So I've already created a folder, my RAG pipeline, and this is where all the magic is going to be happening. Now, the first thing we're going to do is that we're going to set up this folder as with a Python virtual environment. So let us hook it up with a Python virtual environment. I'm just going to say Command-Shift-B. Create environment, yeah, with VMV, and I'm using Python 3.11.6, but any Python version at I think 3.10 upward should be good. So yeah, we have our virtual environment in place. Let me pull up the command line. Yeah, we are inside it, but if you are not in your virtual environment at the moment, you want to make sure that you run source VMV bin activate. So make sure you run that so that you can activate your virtual environment. I think on Windows is something activate inside a scripts folder or something. So yeah, let me pull this aside a little bit. Yeah, it's too big. So yeah, we have our virtual environment in place. I can close out of this. The next thing we're going to be doing is bringing in dependencies or installing our dependencies. Now, to get that done in time, I'm going to create a requirements.txt file and paste a bunch of dependencies in there that I'm going to be explaining soon, so don't panic. This is also going to be available on the repo, so you can get access to the repo and be able to see all this. So we're going to be using LangChain, and as we code out, you're going to see a bunch of things we're going to be using LangChain for. For example, we're going to be making use of the LangChain document type, and also we're going to be using the recursive text splitter when we're doing our chunking. We're also going to be using LangChain community so that we can interact with our vector store. The vector store we're going to be using is ChromaDB, because we can easily use it locally. All the stuff we're going to be doing here is going to be local, but you can host it on your server and you can run it as a RAG pipeline remotely. We're also going to be installing LangChain Chroma to help us interface with Chroma. We're going to be installing sentence transformers from Hugging Face. This is the default model that we're going to be using to generate embeddings, but this project is also going to support being able to use OpenAI or Google Gemini for your embeddings. SQL Alchemy, as you may have guessed, is going to be our ORM. Going to have Pydantic for some data modeling. PyPDF is also going to be brought in because we want to be able to also process PDF files. We want to be able to just dump PDF files in a folder, and our RAG pipeline is going to pick it up and do what it does. Python.env is going to be helping us manage our environment variables, which is basically going to be our keys for OpenAI and Google. And also we're going to be having LangChain Hugging Face so that we can use the Hugging Face models through LangChain, and the same for LangChain OpenAI and LangChain Google GenAI, all to be able to make use of the LangChain's interfaces for their embeddings models. So yeah, those are our dependencies. Now let us install them. I'm going to bring up the command line, and to install that, I'm going to say pip install -r requirements.txt. We hit enter to install that. Now this might take a while, so while that is going on, I'm just going to be creating some other stuff. First, I'm going to add a gitignore file to this. Gitignore, and inside here we're going to ignore our virtual environment folder and our environment folder, a .env folder, or .env file rather, that we're going to be creating later. So let's save that. I've gitignore in place. The next thing we're going to do is create the module folder for our RAG pipeline. So here I'm just going to create a new folder. I'm going to call it RAG underscore pipeline. And inside here, I'm just going to manually add init.py file. And what I'm going to be doing here is going to be defining all the modules I want to make public. Now, there are going to be 3 modules. First is DB, where we're going to put all our database functions. We're going to be using SQLite for our database. That is the database that we're going to be dumping our documents into before we then chunk them and embed them. So we're going to be using SQLite for that. And this DB module is going to contain all the functions that we will need to perform our database operations. Looks like our installation is done. Next, we're going to have an ingest module, and this is where we're going to write all the functions that are going to do the ingest phase, that are going to run the ingest phase, chunk, and all that. So then we have a pipeline module, which, as you may have guessed, every single function that is going to be involved in our pipeline. So later on, we're going to be seeing these modules. So for now, don't dig too deep into them. Our installation is done, and I think that should be all for our project setup. Yeah, that should be all for our project setup. In the next video, we're going to start writing this module. So in this video, we're going to be creating the module that is going to represent the database layer for our RAG pipeline. This is going to contain functions that would help us manage all our database operations. These include functions that's going to set up our database. It's going to ingest our documents and store them. It's going to store them in an SQLite database. But definitely you can use any type of database for your own RAG pipeline. Like I said, I want everything here to run locally. So, and SQLite is just a very, very no-brainer option to getting something simple set up. So let us begin. First, let me close out of these files. And inside RAG pipeline, I'm going to create a new file, db.py. And to begin, we're going to be importing some dependencies. So first, we're going to import JSON. We also need to import OS. We'll also get some utilities from the typing library. Then, because we're going to be working with our SQLite database, we need SQL Alchemy. So SQL alchemy, get column, get integer, get string, get text, and finally we get create engine. And from the ORM, get our declarative base and session. Now, the next thing we're going to be getting is the document object from LangChain. Now, I want to set it up in a way that we can also support older LangChain versions. So I'm just going to say try. Let's say from LangChain core dot documents import document. Now, if you don't get that, we are using an older version of LangChain, just simply create a fallback. Accept, create a fallback and say from LangChain the schema, LangChain.schema import document. Okay. Yeah, like I said, this is just to support older versions. So yeah, I'll just ignore the error there. So the first thing we do, let's set up our base. And then we can use it to define the document table, which I'm just going to call raw document. Say base. Our table name set to, just call it raw documents. Raw documents. And now we can define our fields. So first we're going to have an ID. It's going to be an integer. It's going to be our primary key. And we want it to auto increment. That's good. Next, we want the source of every document that we're putting into our database. We want to know the source. So this will be of type string, and it cannot be null. Then we want the raw content of the document to be of type text, and it can also not be null. Finally, if we have any metadata, we want to store it as JSON, or at least the text representation of JSON that we can then parse later. And this can be null. It's optional. So get all this. Or rather, these are the fields representing our documents table. It's good. Just going to leave that there. And the first method that we're going to be defining in this model is going to be a private method. So I'm going to start with an underscore and say make engine. This function is going to help us create an SQLite database given a part. So give it a part, and can then use that to compose a URI. So SQLite S3. Okay. So the os.part.absolute part, and we pass our DB part. So our DB part in there, and then we can return create engine. Give it a URI. Set feature to true. Okay, good. So we have the function that will help us create our SQLite database. Next, we need a function that can help us set up the table. So for that, I'm just going to say define, it's also going to be a private function. So say, nope, let's make it public. init raw docs db. It's going to take a db part. It's a string. It's going to return nothing. And then here we're simply going to say engine equals, then we'll call our make engine method. No, I don't want that. Make engine method, and we can then pass it our db part. Then we can create our table inside that. Metadata dot create all. That's our engine. Okay, that's good. The next method will be created. It's simply going to be able to take a single document and insert it into our database. So say define insert raw document. You can say db part string. We want the source of the document, of course. We want the content, and we want the metadata. Metadata and metadata can be optional, but it has to be a dictionary. You can also give it a default. So we define this function, which is going to return an integer. Oh, sorry. So it's this, return an integer. And inside here, we can start our insertion process. So first I'm going to get the engine. The engine equal make engine. Pass it our db part. Okay, where is my indentation? Something wrong here. Okay, oh sorry. Okay, so let's go back here and do this. Oh good. So say engine make engine, then we can get our session in a context and say session engine as session. And inside here, we can define a row, which will be a type of our raw document. And here we can set source to equal source. And do the same thing for content and metadata. So I'm just going to bring this here. Content equal content. And metadata would need some processing. So for metadata, because we want to have it as JSON text, we'll just say json.dumps metadata. And if you don't have anything for us, just dump in an empty dictionary. So we have our row. Then we can say session.add and pass it our row. Commit that operation. Refresh. And finally, we can return our ID. So it'll be row.id. Okay, so we have this function. Now, I remember creating this function when I was writing out the version of this, but I don't know whether I used it in the pipeline eventually, but yeah. But anyway, it's a cool function to have around, even if we don't eventually use it. The next function we're going to be writing, which I remember definitely using, is insert many raw documents. But many raw documents, what it's going to take is going to take a db part. It's going to be a string, and it's going to take a docs parameter, which is going to be an iterable. And we just give it anything or something, a tuple that looks like our document. So our document has source, which is string, it has content, which is string, and it has an optional dictionary. Okay, so anything of this shape, and this is going to return none. Keep getting those arrows wrongly. Okay, so here we're going to do a bulk insertion, and the first thing we're going to do is get our engine from make engine, part to the DB part, and then we say wait. Just put a line under that. Say wait session engine as session. As session, and say for source, content, and metadata in docs. Create a new row and add it. So what I'm going to do here, I'm just going to go up here. Well, yeah, this function. By the way, raw document, is this metadata or metadata JSON? Yeah, this is metadata JSON. That's what we defined. Now listen. So I'm just going to copy these lines. Close this. So for each of this, we're going to do this. Create our, let me push this in. So we're going to create new instances of raw document, and we're going to add them. We're going to add them, and we can then, once we're done, we can then commit this. So session dot commit. Okay, so that's good. We have our function that dumps a bunch of documents into our SQLite database. That is the load step. That does the load step. Now let us write a function that helps us fetch those documents from the database. Say define fetch all documents. And this will simply take the DB part. And it's going to return a list of LangChain document objects. So yeah, we're going to be returning LangChain document objects whenever we're extracting our documents from the database. We'll save them with our raw schema. Whenever we're retrieving them, we're going to be retrieving them as instances of LangChain documents so that we can seamlessly use it with our recursive splitter, with our embeddings model, and all the other LangChain interfaces. So first, let's get our engine. Get make engine. I'm just going to copy this. Okay, so get that, and then we'll say documents. Create documents variable to be of type list of LangChain documents, and for now it's just going to be an empty list. Then we'll start a database session. Say session engine as session, and inside here we're going to say rows is going to be a list of raw document, be equal to session dot query raw document, raw document. That's a table or the data model. I'll get all of them. So we'll get all of them so that we can loop over that. So for R in rows, metadata is empty. It's an empty dictionary for now. We'll now say if R dot metadata JSON. So if there's metadata, then we want to try. Let's say metadata be equals to JSON dot loads the metadata JSON. If that happens, great. If it runs into an error, just simply return an empty metadata, or we'll just say metadata, give a default metadata that shows that there was an error. You say meta data pass error. So we're gonna pass the metadata, so that's true. So we have this, and with our R in place, we can simply create an instance of LangChain document and append it to document. So say documents that append rather, not appends. Look at append, then we create an instance of LangChain document. Say document, the content is represented with a property called page content. It will be our r.content. And put this in separate lines. So we have this. Then the next is metadata. Metadata, which will equal, we have source, to be set to r.source. And then we can just mix in the remaining metadata. So we have that in our document. This is our document definition. We are appending it to our document array. And once we're done with that, we can jump out of this and return documents. Return documents. Okay, so those are our functions. That's our database layer. First, we have our make engine function that defines or returns our database. Then we have the init raw docs db method that sets up our database with the raw documents table. We have our insert raw document function, our insert many raw documents function that bundles a bunch of documents into our database in the standard format, that's raw document, and also fetch our documents that fetches our documents and returns them as instances of the LangChain document type. So these are our functions on the database layer. Let's see, we still have this. I'm not expecting this to cause an error, but if it does, we'll just find a way to deal with it. But yeah, this is our database layer. And in the next video, we're going to be writing the functions that are going to be doing all the ingestion for us. So in this video, we're going to be writing the functions that are going to be helping us to get our files, all the files that we put in a specific folder, get all those files, passes them, and save them in our database. These functions are going to help us extract the contents of our files, create the metadata, and store them in our SQLite database. We would be supporting text files. We'll also be supporting markdown files and PDFs in this particular demo, but definitely you can always build up your RAG pipeline to be more robust and support even media like images and videos. Now these files are going to be saved as standard documents and returned as LangChain document types, as we've seen in the previous video. So without much ado, let us get started and create our ingest.py file. Let's create that. And let us get in some dependencies. First, I'm going to be bringing in pathlib. And from there, I'm going to get our path. Then also from typing. From typing, we're going to say import dict. We need lists. We need optional. And we need tuple. Okay, so we need those. Then from the module that we just created, the DB module, we're going to be importing the init raw docs DB and the insert many raw documents methods. So that's from this module that we created in the previous video. So we're getting these two. That's cool. Next, we're going to create constants for our supported files. So first, for our text files or files with text extensions, those will be our .txt files and markdown files. So that's for our text files. Then also for our PDF files, so PDF extension, and just set it to a string, say .pdf. Okay, so these are going to be our supported file extensions. Like I said, you can always build up your RAG pipeline to be more robust than this, but for now we're keeping things simple. So let's start creating our functions. The first function we're going to create is going to be an internal function that we're going to call read text file. I'm simply going to take a path to that file and return the string content. So here we'll simply in one line say return path dot read text. I want to read in UTF-8, and if there are any errors, just simply ignore them. Simple, straightforward function. The next function we're going to be creating is the one that will read PDF files. This one is just for our markdown and for our txt files. So next we're going to be creating the one that's going to read PDF files. So I'm going to say define underscore read underscore PDF underscore file. Also takes a part of the type part, and it will also return a string. No, not that. String. Okay, good. So it returns a string, and here the first thing we're going to do is to import PyPDF. We're going to be importing that inline. So I'm going to say try from PyPDF import the PDF reader. Now, if you encounter a problem bringing that in, we're simply going to say raise runtime error. I'll say PyPDF is required to read PDF files. So install PyPDF. Install PyPDF. Yeah, we'll just say from E. Okay, so once we have that, now we're setting the function. Once we have our reader, we can say reader equals PDF reader, and pass in our paths, which are going to cast into a string. Then we get the texts from that. Put them in a list of strings. Set this to empty for now. Then we loop over our results. We'll say for page in reader.pages. For page in reader.pages, the first, need to add, yeah. So we'll try appending the text that we got to our text list. So we'll say page.extract text. If not, give us an empty string. Let's say accept. Just add an empty string. Okay. Then for all the text that we get, we want to return them by simply joining each and every one of them using a new line. So the join texts. Okay. So we have this function. Looks good. Let me come out of that function. Close it up. Now the next function we're going to be creating is a function that would help us go into our directory where we have put in all our files and just gather them, gather their parts, and return all those parts as a list so that we can process them and eventually have them embedded and stored in our vector stores. Now we're going to write this function in a way that it is going to recursively go through a folder and gather all the files there, all the files that we want it to get, the files that are supported. So it doesn't get any, let's say we have a music file there, it won't bother to get that. So this is going to have our source directory, that's a string, and it's going to return a list of parts. Now, the first thing we're going to do is get the roots of our source directory folder. Source, I'm just going to copy that from here. Let's copy that source dir to get the roots and check if it even exists. So if not roots dot exists or not roots that's if it's not a directory. So if it doesn't exist or it's not a directory, we want to raise an error. So simply say raise file not found error, and here we'll simply put a message that says source directory not found, and we just indicate which source directory we're talking about. Okay, so we have this here. Then if all goes well, we'll define a parts variable. There's a list of parts. It's going to be empty at the start. Then we can then recursively go into our directory and find all our files and directories. So say for p in root dot club, just pick all the files that you find there, files and directories you find there, and here we're going to check if we have a file. So first, if this is a file, and if it is a supported file, so p dot suffix dot lower, if it's in text extensions, just copy that. So if we have these in text extensions, or no, it's not uppercase, or the suffix is actually equal to PDF extension. So if it's a PDF or if it is inside our list of text extensions, then we will know that it's a file that we are interested in, and we'll simply append it to our part. That's good. And once we're done with that, we can simply return our parts. Awesome. That's awesome. So now we have this function that helps us to gather our files from our directory, and we're going to be writing, I think, yeah, this should be the last function. So the last function we're going to write, which is actually going to be making use of all this, is the function that is going to initialize the document database, gather all the files from our directory, extract the file contents and metadata, and then insert them into our database. Yeah, it's going to do all the entire load step. The entire load step. That's what it's going to do. So yeah, let us see what that looks like. So define ingest files to DB. Files to DB, and this is going to return an integer, which is just going to be the number of documents it was able to put in our database. So source directory, DB part, and it's also going to take, DB part is going to be a string. It's also going to take a default metadata. Metadata is going to be optional. Ticked and none by default. So we have this function which is going to take all our files and put them in our database. So the first thing it's going to do, just step one, let's start putting steps now, because we're beginning to actually code out the different steps in the two phases that we described in the conceptual video. So first is to initialize the SQLite database. That's the first thing to do. I don't have this trailing, whatever. So we're going to call the init raw docsdb. That's this guy. So get this guy, and we'll simply give it our db part. Good. Give it our db part. Then step 2. Second step, we're going to gather all supported files from the source directory. And we know the guy that's going to do that. So what we do is we create a variable called files. We call gather files. And we'll simply give it our source directory. Source directory. That's good. Now for the third step, step 3. And step 3, we're going to read the content of each file and insert it into a list of tuples. Cool. So let's get on to that. So say rows, there's going to be a list of type tuple. And tuple is just simply going to be in the shape of our expected document. So can both support raw document and LangChain document. So dict, yeah, this will be empty. So here we'll simply just say for f in files, because we've gotten our files now. For f in files, first we check if the suffix shows, no, sorry, the suffix shows that it's the text extension. So that is the text extension. Then we need to get the content using our read text file function. So we get read text file and pass it f. So that's good. Else, if this guy is equal to PDF extension, then our content, oh yeah, I didn't get the tab in. Then our content is going to be retrieved by the read PDF file function. So do this and give it f. It's good. Else, if it's none of these guys, we're just going to continue. Then down here, we create metadata. Set our metadata with our file name, which will simply be f.name. And we'll just simply spread the default metadata, or just give it an empty dictionary. Okay, so metadata done. Then say rows that append string. Now we're gathering rows to put in our database. So string f content metadata, which is everything that represents our raw document type. And once we're done with all that, we can then check. This is step 4. Step 4, where we insert the rows into the SQLite database. So here we first check if we have any rows to begin with. If so, we would call our insert many raw documents, because we have a bunch of them we want to insert. and give it the DB part and our rows. Get that. And finally, from this function, we're just going to return the total number of rows that we have. So yeah, that was quite a function. So basically, we initialize our SQLite database. We gather our files from the directory that you're going to see us create later and put a bunch of files inside that we want to use for our RAG process. Then inside that directory, we check our files. If it is of the text extensions that we marked out here in text extensions, then we want to use this function to read it. If it's a PDF, we want to read it with this function. And then we build our metadata. Then we append our information as a row. By the way, I think an extra set of brackets is needed here. Yep. Okay. So we add this tuple into our rows, and then we can then pass these rows inside the insert many raw documents function, which basically helps us to load it into our SQLite database. And finally, we just return the total number of rows that we got. So this is all good. And now, yeah, I think we're done with this module. Yeah, we're now done with this ingest module. And in the next video, we're going to be writing the pipeline. So we've written the functions that would take our documents from our directory, our source directory, and load them into our SQLite database. That's good. That's a load step. Now we need to create the functions that are going to take those documents in our database, chunk them, embed them, and then store them in our vector database. So these are the functions that are going to complete the ingest phase, the ingestion phase. That's what we're going to be creating. So we're going to be creating a function that helps us to split our documents. We already have the function that is going to help us fetch all our documents from the SQLite database. So we're going to create a function that is going to help us split our documents. Another function that is going to help us, that's going to return the embeddings model we're going to use. Then that will then be used by another function, which is going to create the embeddings and store them in our embeddings database. We're going to be using a Chroma store for that. And we're also going to be creating some other functions that are going to return an instance of our store and also our retriever. Like I told you, each store can get you a retriever that you can use to query the contents of the store. So I'm going to call this pipeline.py. That's our third module file as specified in our init.py. And then inside this file, the first thing, like we always do, we import dependencies. So I'm going to be importing pathlib. And from there, I'm going to get part. Then from typing, I'm going to import iterable list, and optional. So get that. Then I'm also still going to do my weird lang chain stuff that I'll probably remove if it doesn't work. Yeah, I'm going to do this once again. Then, like I said, we're going to need to split our documents. Once we get them, we need to split them because you can't just embed, for example, an entire book. You can't embed the entire book. That is not going to be performant. That's not going to even work fine. So to help us do that, we're going to also seek the help of langchain. So from langchain text splitters, we want to import the recursive character. These are always a challenge to spell correctly. The recursive character text splitter. Oh, blue, good. So we're right. So recursive character text splitter. Then also from langchain chroma, going to import the chroma class. Also from langchain again face, again face. We're going to import the again face embeddings. Okay. Also, because we can use OpenAI, so from langchain OpenAI, we're going to import our OpenAI embeddings. And from LangChain Gen AI, I'm going to import the Google Generative AI embeddings. Okay. Finally, we'll just import ChromaDB. So those are our imports, and we can get to work. Next thing we're going to do is create a constant that's going to represent our collection name. That's the collection that is going to be in the vector database. So the default collection name, I'll just call it rag docs. You can give it any name you want, but for this demo, we're going to call it rag docs. Now, the first function we're going to create, like I said, is going to be the function that will help us chunk our files. So it will take a file, it will split it into chunks so that the embedding process can happen in chunks. So we define that function. I'm going to call it chunk document. It's going to take in a list of documents. Then it's also going to take in a chunk size. That's the size of each chunk. You can specify this to be anything you want. I'm going to give you the default of 1000. So the chunk size is how large you want each chunk to be. It's more like how big you want each piece of context that can be retrieved to be. So if it retrieves like 5 documents as context, how large do you want each document to be? Next is going to be chunk overlap. And like I explained earlier, this is important for you not to lose context. If you don't want to lose context within documents, you don't want, for example, if a document starts abruptly, if you slice and dice documents, some documents can start with, let's say it's a document about rainfall, and it just start from a point that says the humidity is about 25 degrees. And you'll be like, the humidity of what? What are you talking about? So, or a document starts correctly, or rather starts from the beginning, or starts from a place that is understandable and says rain falls in the Sahara Desert only once, and it just stops there. Only once. Only once in what? Only once in what? So sometimes the overlap helps to do that. So the document that precedes that starts abruptly, let's say only once, then the next document says in a month and whatever. So you can create an overlap that would help those documents to at least make some more sense. And especially when they are read together, they can know that, yeah, these two documents connect together, and yeah, this is how it actually reads out. So that's what you use the overlap to do. Let us do the return for this. This is going to return a list of documents, but now it's going to be chunked documents, not the full documents. It's going to return a list of documents, and inside here, we're simply going to say splitter equals, then we get this long name stuff, our recursive character text splitter from LangChain, and we supply it with this element. So first we give it chunk size. Give it chunk size, and it's going to be the chunk size that we defined or that we passed as argument. We also give it chunk overlap, which is going to be the chunk overlap that we passed in. Then the length function, the function we want it to use to calculate its length should just be the standard length function from Python. Okay, so, and we can simply then return the operation of this splitter. So we'll say splitter.split documents, split documents, then we pass it the documents. So that's what is going to be returned. It's going to return the list of documents, but this time it's going to be chunks. It's going to be document chunks, but they're still going to have the same document shape. That's the LangChain document type, the same shape. So we have this function that chunks our documents. The next function we're going to create is a function that returns the embeddings that we want to use. Like I said, by default, we're going to be using the Hugging Face embeddings, the one that we imported, or rather, the one that we installed, which is sentence transformers. Going to be using that by default so that we can just run this RAG pipeline without having to pay OpenAI or get an API key from Google and stuff like that. but we also want to be able to use OpenAI or Gemini if we want to. So this function is going to simply get the embedding that we would like to use. So say define get embeddings, model name to be a string, and we're going to default that to a Hugging Face model, which is a sentence transformers, and the model will be all mini LM L6 v2. Yeah, that's going to be the default model. Then the provider, there will also be a string, and the default will be Hugging Face. So that's good. Now let us write this function. First, I'm going to set a p variable that we'll use to check if we have a provider. So if we have a provider, that will be fine, but if we don't, then it should be set to Hugging Face. Hugging Face should be our default provider. Say dot lower, and then we can loop through. We'll say if our provider is OpenAI, then we'll create a variable called chosen, which will be our chosen model. So chosen is equal to model name, just model name, and we'll check that model. If the model does not exist, or the model starts with something that looks like an Hugging Face model, that is sentence transformers. If it starts with something that looks like an Hugging Face model, then we should set this by default to OpenAI's text embedding 3 small model. That means the person passed in OpenAI as the provider name, but somehow they left the model as the default, or they passed in an Hugging Face model. So we'll just give them a default OpenAI model. However, if they actually passed a correct OpenAI model, then we can go ahead and just return the OpenAI embedding. So model equals chosen. Model equals chosen. So if they selected OpenAI as their provider, but they didn't pass any model, or they passed in a model that looks like Hugging Face, then we set the default OpenAI model that they are to use to text embedding 3 small, and then we return the OpenAI embeddings. But if they actually did set a model that is an OpenAI model, then this still applies. This still works. So that's fine. Now, if, or elif, or let's just do an if. If we are using Google, if they set Google as their provider, then I'm just going to repeat this and just change some things. Just going to copy all this. The model is going to be set to the chosen variable, and if they didn't set, or rather if this is null, or it starts with a Hugging Face type of signature, then we want the default Google model to be models / text embedding 004. And if not, or rather in both cases, whether they got it right or not, we want to return Google generative AI embeddings. Yeah, that's correct. Generative AI embeddings. So we're just trying to make sure that we don't set the wrong model name here, or set an Hugging Face model name for a Google or an OpenAI model name. So this is fine. However, if they did not satisfy any of these conditions, simply return the Hugging Face model. I will have to copy this. These are long names. So Hugging Face embeddings. So simply return the Hugging Face embeddings, and the model name should be equal to the passed in model name. Okay. So this is fine. We can, by the way, to use this models from OpenAI or Google, we need to set the environment variables, that's the API keys, but we're going to be seeing that later. So the next function we're going to create is a function that builds our vector store, and it builds it with the documents that we embedded. It's going to embed documents, then it's going to build our store with these documents that have been embedded. So let's do that. We're going to call this define, and this will be build vector store. Vector store. So this is going to take our chunked documents, which will be a list of LangChain documents. It will also take in our embeddings model. Just going to call it embeddings, and we're going to also take the name of a directory that we want to persist the vector store to. So the optional string type none or default none, and it's going to return an instance of Chroma or ChromaDB. Okay, so let's begin. First, we're going to start by defining our Chroma client, which we'll set to none for now because we don't have it. Then we'll check if we have persist directory. If we have persist directory, then I'm going to use the path module to persist to this directory. We'll make the directory, we'll create directory, parents equal true, and exists. Okay, true. We'll then say client equals ChromaDB dot persist client. Then we set the path to equal persist directory. So we create that path and we set our client to persist our Chroma database to that path. And once we have this, we can return a Chroma instance that's going to be generated from documents. And first, we give it our chunked documents. We give it our embeddings through the embeddings parameter. That is the embeddings that is going to come from our get embeddings function. So it basically needs the instance of the embeddings model. Then we'll give it our client, which is going to also help in persisting the ChromaDB. Then our collection name is going to be our default collection name that we created earlier. Default collection name. Get that, put it here. And the squiggly lines are gone, so we're good. And we have our build vector store method. Awesome. Our next method we're going to be writing is the one that is going to help us load the vector store that we created. Just basically returns that instance for us. This builds it, then we have another function that can give us the instance anytime we want. So I'm going to call it load vector store. Vector store, I'm going to take a path and embeddings model. Now, one thing about vector stores is that the same embeddings model that you use to embed documents into them must also be the embeddings model that you use to call out those documents. You can't use OpenAI to embed documents into them, a particular OpenAI model to embed documents into them, then use a Google Gemini model to want to retrieve those documents. That is not going to work. So the same embeddings goes in and out. So for this, we're going to also return a Chroma instance, and first we get our client. So client equals ChromaDB dot persist client. Give it our path. We can then return our Chroma instance from this using our client. So Chroma client equals client collection name, just a bunch of stuff from here. Collection name, just copy that from build vector store. And finally, we'll have the embedding. Now here we have embedding function. Embedding function equals embeddings. That's good. This function is done. And finally, we're going to write a function that is going to give us our retriever. Our retriever is what takes our user query and goes into the vector store to help us pull out documents that match the user query, either keyword match or semantically. Let's say define get retriever. Then this will take a vector store, which will be of the chroma type, and it will take a k parameter, which is like our top k. So these are going to be our top k, which represents the top embeddings to return. Top results. So if you want 5 results, if you want 10 results, this is what you set. For now, we're going to just return 4 by default. You can always specify this, as we're going to see in the build run. When we start running the build, you're going to see that you can specify this at runtime. So search keyword arguments, and here we only provide k. This is also the point where you can provide the type of search you want to perform, whether it's semantic or keyword. So yeah, this is good. We have these functions, and we should be done with this module. Should be done with this pipeline module. That's good. Now in the next video, we're actually going to be running the pipeline. So we have all the functions that we need. Now we're going to be writing our main file that now we can take all these functions and run those steps that we looked at when we are looking at the How RAG Works video. So that comes up next. So we have written all the functions that we need for our pipeline, and now we can actually write out the pipelines. Now we're going to be writing 2 pipelines, and they are going to represent the 2 phases that I talked about in the video where we're explaining how RAG works. We're going to have a build pipeline, which is going to represent our ingestion phase. So that is a pipeline that is going to take our files from the folder. We're going to have a folder where we can dump files. So we're going to write a pipeline that is going to take those files, is going to load them into the SQLite database. Then they're going to be picked from the SQLite database. They're going to be chunked. They're going to be embedded, and they're going to be stored in the vector store. So we're going to write that pipeline. Then we're also going to write the generation pipeline, which is the pipeline that is going to take a query, go and search our database, our vector database. By the way, let me just start doing something so that you can know that I'm here and your screen is not frozen. So we're going to write the pipeline that is going to generate, or rather that is just going to take our prompt and go into the vector store and bring out matching documents. Later on, you can tie this to your LLM to actually make a prompt return a response, but we're just doing pure RAG here. So we're just going to be stopping that at the point where we go into our vector store and we get chunks of document that relate to our query. So let us begin. This is going to be our main file. This is going to be our entry point file for this RAG pipeline module. And inside here, we're going to start the same way we start with every other file, which is by importing dependencies. So first we bring in argparse, because we're going to be running our build from the command line, and we're going to be passing it a couple of options. Then we're going to say from typing, we want to import optional. From pathlib, we want to import part module. Then from .env, we want to import load.env. So get those in place. Those are from the standard library and from our installed packages. Next, we're going to be importing stuff from our pipeline files. So from .db, we're going to import fetch all documents. Yeah, that's the guy that's going to be getting all our documents from the SQLite database. Then from ingest, we're going to import ingest all files to DB. Was that the name? Ingest all files to DB. Was that? Let me check the name. Yeah, that's it. Ingest. Oh, there was no all there. Sorry. Ingest files to DB. Yeah, ingest files to DB. So then from pipeline, we're going to import a bunch of stuff. So first we're going to get our build vector store. Then we're going to get chunk documents. We'll also do get embeddings, get retriever, 1T, get retriever, and also load vector store. Vector store. So get these guys, and we're going to be using them to run our build pipelines. So we have all our dependencies. Now let us write the first pipeline, which is our build pipeline. Now say build pipeline. Build pipeline. Okay. So I'm going to say this will be def run build. And this is going to take a bunch of arguments. First is our source directory, which is where our documents are going to be stored. Then our DB part, which is where we want to store our SQLite database. Then our vector is going to take vector store part also. This is where we want our vector store to be stored. Then chunk size, an integer. We also want chunk overlap. Chunk overlap, which will also be an integer. Then model name, which will be a string. And then our embeddings provider, which is basically the provider for this model name. Embeddings provider, and that will be string. This is going to return none. It's a pipeline, so don't want it to return anything. And now we're going to run our build. We're going to run our build in steps. So step 1, we want to pull our source documents into a database. So to do that, what do? We're going to say count and call ingest files to DB. I'm calling it count because I know that it's going to tell me, it's going to return the number of files that are ingested. So ingest files to DB, it takes a source directory, which we're going to set to the source directory that we passed in. And it also takes a DB part for our SQLite database. I'll also set that to the DB part that is passed in. Okay, so once we have that, let's print something to the console. Say ingested count files into SQLite database at DB part, not DB plus part. Okay, so we have that in place. It's ingested this total amount of files into SQLite database. The next thing we're going to do, which is going to be our step 2, is that we're going to pull data into the RAG pipeline by first chunking them. Okay, so what do? First, we get our documents from our database. So I'm going to call fetch all documents. Where is that? Fetch all documents. Just get that from our database. We'll pass it the DB part. And then we're going to add the print statement, just to tell ourselves what we're doing. So we'll say fetched this amount of documents, and this amount of raw documents. Documents have not been sliced and diced yet from DB. Okay, so now let us chunk them. So let's say chunks equals, let's get chunk documents, split them. So pass these documents, the chunk size will be the chunk size that we passed into this function, and the chunk overlap, they're the same name, so I'm just going to repeat them here. Chunk overlap is going to be chunk overlap that we passed in, and yeah, those are the arguments. So let's put another print statement here. Here we'll say created this length of chunks, this amount of chunks, created this length of chunks. Okay, it's good. Now step 3, let us embed and put in our vector store. So embed and save your documents in a vector store. Vector database. By the way, if you want to see me build this pipeline to also support pulling files from S3, let me know in the comment section. Yeah, let me know that. I should have mentioned that in the beginning. But yeah, if you want to see me do that, I'm also trying to automate this whole stuff with ZenML. So if you want to see that too, let me know. ZenML, I'm currently facing a blocker where ZenML does not work very well with Chroma, and I need to kind of create a whole interface, call it materializer in ZenML for that, and still working on that. But if you want to see that also, let me know in the comments. So embeddings model, first let us get our embeddings model. We'll say get embeddings, and we're going to pass it model name, which will be the model name from here, and also pass it provider, which is going to be our embeddings provider that we passed as the argument into this build function. So that gets us our embeddings model. We can then use this, and then use this to create our vector store. Just going to vs equals build vector store. Let's get that. Build vector store, yeah. Build vector store, and it needs the chunks, the embeddings model. Yeah, that's this guy. It's the embeddings model, the persists directory. The persist directory is going to be our vector store part. So let's get that vector store part, and I think that should be everything. So after this process, we can also put a print statement here and say saved Chroma vector store to the vector store part. Yeah, to the vector store part. So this is good. These are our build steps. So we go from getting our files as ingesting them to then pulling them out, embedding them, and using them to build a vector store. Perfect. So let's collapse this function. This is for the build pipeline. How about our generation pipeline, or let's say our query pipeline? For that, I'm going to write a new function called run query. Like I said, this is the write step, this is the read step. So this, you only run this once when you have a set of documents. Whenever you have a new set of documents, then you can run it again. But this step will be run each time you want to prompt your LLM. Then you want to prompt your LLM, you have to run this step so that you can get your embeddings that will form the context for the user query. So let's write this. Let's write run query. Run query is going to take vector store parts. I'm just going to be copying a bunch of those from here. So vector store parts. Then it would also take a query parameter, of type string, to take model name. Do we have model name here? I think we do. Take model name. Does it take embedding provider? Yeah, it takes embedding provider. So we'll just copy these two. So model name and embedding provider. That's good. So with all this in place, yeah, it still takes one more thing besides this. We need our k, which is going to be int and 4 by default. And then this would also return none like its counterpart. So with all this in place, we have the embeddings provider, we have model name. So the first thing we want to do when we want to retrieve our context from a vector store, first we get our embeddings model. So let me just get that from here. Model name, model provider. Then we load our vector store. We get our vector store. So we call load vector store, which you can find here. Call load vector store. We pass it our vector store part and our embeddings model. So vector store part and embeddings provider. No, the embeddings model itself, not embeddings provider. Embeddings model. So like I said, you have to make sure that you're consistent with your embeddings model. The embeddings model that you use to embed your documents into your vector store, that's the same that you use to retrieve it. To actually retrieve, we need to get our retriever. Get a retriever, and we can call get retriever for that. That's, I think, the only import we're yet to use, aside some guys from up here. So it's a get retriever, and from get retriever we pass it a vector store and we pass it our k value. That's the total amount of documents we want to retrieve. Then we can say docs equals retriever dot invoke, just like any LangChain runnable, dot invoke, and then we can pass it the query. We can pass it our query, and then we can print our top documents. Say top documents, and those will just loop over what was gotten. So that will be for I and D as document in docs. Let's put an enumerator around that so that we can get the keys to, or indexes. Enumerates docs start from 1 and not from 0. And here, first thing we want to get is our metadata. So I'm just going to say meta equals d dot metadata or an empty dictionary. Then here we're just going to print. I'll say I. That's the count of our document. I think, yeah, let's put I inside curly brackets. So I, and we'll say meta dot get. So if we have the source, we would like to see the source. Else, just say unknown. So source is supposed to return things like the name of your file, so you can know where a particular result is coming from. So if you have a file name, let's say ragdocs, you can be able to spot that when you see results from it. So meta.get, again, we would like to get a file name. And there. Okay. So we have this, and the content itself. These are LangChain documents, so they follow the LangChain document signature. So we can also get the content from page content. For now, we'll be restricting this to the first 500 characters. And I'm just going to put some dashes here as a delimiter for each section. So yeah, we are getting, these are our run pipeline. And these are we get our results by passing in a query. Okay, so we're done with our two pipeline functions, the build function and the run function. Now, but how do we actually run this? How do we run this? We're going to create a main function to run that. And we'll be able to run this from our command line. So here the first thing we're going to do is make sure that we're loading all the environment variables from our .env file. That's .env file that will be containing API keys for OpenAI or Gemini. So for that, first let me put a comment and say load environment variables for API keys. So for that, I'm just going to first get the project root. Say path, the file we're in, let's resolve. Let me say that parents 1, and would say /.env. /.env. Then we can then load .env and say .env part equals our project root. The project root. So we're going to the parents because we're inside the file. The main file is inside this RAG pipeline. So we want to go up and then get .env from there. So we get this. And that's good. Now, to run our pipelines, we're going to be passing the expected arguments of the pipeline through our command line. We're going to pass it through our command line so that we can change all these values at runtime. We don't want to put them in code. Another thing you can do is probably pull them from something like a YAML file, any kind of strategy you want to use, but we're going to be using the command line and passing them as command line arguments. So all these are going to be defined as arguments that we can pass on the command line. Now to do that, we already imported our arg parser, so we're going to create an instance of that. I'm going to say parser equals arg parse, dot argument parser. The argument parser, I'll give you the description. Set that to RAG pipeline demo. Our pipeline demo. That's good. Now we're going to be defining the pipeline arguments for the build pipeline. Let me put a comment there. Say build pipeline arguments. So we're going to be defining this. Now it's a bunch of typing, and I won't want to bore you with all that. So I'm just going to bring it in, and we're just going to walk through it. So copied. By the way, you can get this in the exercise files. That's the GitHub repo. So got this, and it's in. Yeah, getting some squiggly lines here, but I'm just going to do this and do this, and that should be gone. Yeah, just shifted it back and forth to make sure that the indent is kind of uniform. So what do we have here? First, we have our source directory. Like I said, it's going to be the arguments from here. So that's 1, 2, 3, 4, 5, 6, 7. So if we scroll down, first we have source directory. It's going to be a string. The default is data. So you can put your files in if you put your files in a directory called data at the root of this project, that's just what it's going to pick up. But you can specify a particular folder. Then your DB part, the default is going to be rag raw docs.SQLite. Vector store part, the default is Chroma store. Chunk size, the default is 1000. Chunk overlap, the default is 200. Model name, the default is the Hugging Face model. Our model provider, the default is Hugging Face, and we also have a list of choices so that we don't specify something that is not amongst these options. So yeah, this is for the build pipeline. Now let us bring the ones in for the query pipeline. And as you can see, we are putting some help here so that it can actually explain what these arguments are. But like I said, next let us do our query pipeline. Query pipeline arguments. So just as with the build, I'm also going to bring those in and paste it here. For the query, things are quite simple. The main things we need to bring in are the query and the key. Yeah, our query and the key. Those are the main things that we need to bring in. So the query is what we want to, is actually our user query, what our user typed into the prompt. So that would first go into our vector store, pull the matching documents based on the type of matching we're doing, whether keyword or semantic. Pull the matching documents, and then we can bundle it up with our user query as the full prompt that goes to the LLM. Then we have our K, which is the total amount of records that we want to return. So with this in place, let us get our arguments. I'm going to say args equals parser. That's the arguments that we typed in. Parser, parse args. We get those. Now we need to differentiate whether whether the user is running a query, is running the query build, or whether is running the query build or the build, or the query pipeline or the build pipeline. So yeah, we need to differentiate whether we're running the build pipeline or the query pipeline. So to do that, I'm just going to check if the argument contains query. If it contains query, then definitely we're running a query. And that's the one we're going to be running all the time, or most of the time rather. So args dot vector store path. So args dot vector store path. To run the query, we need the vector store path. Where did I have that? Yeah. Vector store path. We also need to, let me just put them on lines, on individual lines. We also need to get args.query, args.model name. Some of these have defaults, so even if you don't pass them, the defaults will just take effect. Args.model, we have model name already, so the next we need to put is embeddings provider. Embeddings provider, then args k. Okay. Oh, sorry. Args k. Yeah. Just k. So if we have a query, we just run query. Else, we run build. Run build. To save time, I'm just going to paste that in here. So yeah. Run query or we run build. Here we're just simply passing it positionally, but here we are using keyword arguments. So either way is fine. Either way will work fine. So now to run this, let's get out of our main function. We'll say if, still need more space. So say if the name is equals to main. Basically, we're saying if this file is run directly, not imported, then we want to just run the main function. Want to run the main function. So run this, yeah, and yeah, that's it. That's it. Run this. This is our entire entry point. This is our entry point where we get to run our two pipelines. Our generation pipeline, which is the build step, or rather our build pipeline, which is run build, our generation pipeline, which is run query. So these are the two. We've written all the code, and in the next video, we're going to be testing things out. So we have gotten to where the rubber meets the road. So far, we have been writing so much code. We have not tested out anything. We don't have squiggly lines except for some warnings around here, so feeling pretty confident about our test. And what we're going to be doing is that we're going to be running this pipeline in this video on a bunch of documents. Now I have created a folder at the root, which you should also do. I named it raw docs, but you can call it anything you want. We're going to be specifying it when we're running the pipeline. Call it raw docs, and they are RAG documents. I'm trying to stay consistent. So they're actually documents that talk about RAG. I have here advanced RAG. This is the V8 advanced RAG white paper. Is a very lovely resource if you want to learn RAG. If you want to go into the advanced chunking strategies and RAG with ranking strategies and all that stuff, some of the things I mentioned in my cheat sheet, yeah, you want to dig into this resource. So you can get it from V8. They have a bunch of wonderful stuff there. I also have a markdown document here, which is also from V8. It's basically their blog on RAG, Retrieval-Augmented Generation by V8. So you can what I did with this was that I got the URL of the blog and I just put it into Gemini to give me the markdown format, because I want to test it as a markdown file. So it just generated the markdown and I was able to save that and put it here. So we're going to be seeing how our RAG pipeline works. We're going to be splitting this document, we're going to be loading them, we're going to be splitting them, we're going to be embedding them, and we're also going to be querying them. So these are the two documents that I'm putting there, just limited documents for now. When you're doing your test, you can put more documents there. I've also added the .env file. I'm not going to open it because I have some sensitive keys there, but you're going to see the this is where you put your OpenAI API key and your Google Gemini key. For OpenAI, you put it with the standard, you use the standard OpenAI environment variable, which is OpenAI _ API _ key. And for Gemini, you use Google _ API _ key. So that's how you set it. I actually want you to do this, and let me know how the experience went doing it on your own time. I'm not sure if I'm going to test it in this video. I might test it, I might not test it, but just do it and let me know how your experience goes. But enough talk. Let us run these pipelines. So I'm just going to close out of this. Okay, yeah. So make sure you're in your virtual environment, very, very important. And the first pipeline we're going to be running is the build pipeline. We're going to be running the build pipeline. So to do that, I'm going to say Python -m so that I can run my RAG pipeline folder as a module. So RAG _ pipeline pipeline.main. That's my main file that is inside here. And the first thing I'm going to be defining is my source dir, my source directory. So I'm going to put a / here so that I can go multi-line. Then I will say my source directory is raw docs. That is where I put these two files, the markdown file and the PDF file, raw docs. Then go once again, and the next is going to be my DB part. That's the part for the SQLite database. I'm going to call it raw. We got a RAG _raw _docs .SQLite. You can give it any name you want, and you can add the .SQLite extension. So that is the DB that's going to be storing raw documents. Next is the vector store part. The vector store part, just put it in a folder called Chroma store, Chroma _store rather. Then let us also define the chunk size. Going to set the chunk size around 1000. And for the overlap, say chunk overlap. And I'm going to set that to 200. So I'm going to stop here. And why I want to stop here is that I can still go ahead and specify my model provider, my model name, but I want it to use default. I want to use the Hugging Face model. So we're going to run this. We have source directory, we have DB part, we have vector store part, we have chroma store, we have chunk size, and we have chunk overlap. So we're going to run this as is, and it will assume all the other parameters. Like I said, it's just two parameters, which is the model name and the embeddings provider, which we know we have defaults for, which is Hugging Face. So let us see how that runs. So that runs. Okay, I've gone down a little bit. I'm just going to hit enter, and we're going to wait. It's going to take as long as the amount of documents that we have. So if you have if you just dump a bunch of documents there, that's going to take a while, and that's where you might want to add like loading indicators just to show that something is going on in the background and there's a progress and all that. But we have just two files, so just in a few seconds we should get back our results, which is the print statement that we wrote. I think it takes more time in loading the documents itself and trying to get it into the SQLite database, but the chunking, splitting or chunking process and the embedding process is pretty fast. So should be done in any time from now. So as you can see, our SQLite database has been created. So that part is being done, and we are seeing some prints here. It ingested two files into the SQLite database. Now it's doing some things, and yeah, got an error here. Let me just pull this up. See what we got. Created 59 chunks, and then we got an error. It says got an unexpected keyword argument exists. Okay, let us find that. Let me just, I know where we used that. Just trying to, yeah. Now pipeline. So let us look at this file. Exists. Okay. Let me check that. Okay. So I definitely misspelled that. It's exists. Okay, not exists. Okay. So, yep. We need to run that again. And just save this. Go back to our file explorer. I'm trying to do that. Let me clear this. So I'm just going to delete my SQLite database. I'm going to delete this so that we can run the process all over again. This is fine. We have corrected the issue we have here. So let's just run the command once again. So here we can see files are being ingested. We have our SQLite database here. Our chroma store has appeared, and we got another unexpected keyword. Yeah, we seem to be getting errors, which is a result of typing a lot of stuff without testing anything yet. So chroma embeddings, I think my high kind of caught this somewhere. Chroma init got let's see, this should probably also be inside pipeline, so let us check that. Embeddings. So when we are building the store, it's actually embedding, not embeddings. It's very easy to get all these things mixed up. So it's actually embedding, not embeddings. So that is something to take note of. Let's pull up once again, clear. And this time we see our chroma store created, but we'll definitely need to get rid of that to test all this over again. So yeah, let's test this again. So run the command again, and hopefully this time we don't have any issues and our code runs just fine. Okay, so finally we have everything working fine after fixing a few errors. We ingested two files into the SQLite database because we have two files here. We fetched two raw documents from the DB, definitely. Then we created 59 chunks. So 59 chunks were actually created from these documents, and they were saved to the chroma store. So we have our SQLite database here, and we have our chroma store here. Now you don't have to touch these files. You don't have anything to do with them, so just leave them. So that's good. But let me not clear this. So now we have our documents inside the vector store, and we can query it. We can now query it. So let us see how we can run the generation pipeline. let's say we can run the generation pipeline. To do that, I'm just going to say python -m rag underscore pipeline dot main, and I'm also going to put the backslash so that I can go multiple line. First, I'm going to define my vector store path so that it knows where to look at. So vector store path is going to be chroma store, just in case you have multiple. So I want to know which one to look for. Chroma store, then our query, which is the main thing that differentiates these two pipelines, the build pipeline and the query pipeline. Now this is where we ask it a typical question like what our user will ask. So let us say our user asks, what is Retrieval-Augmented Generation? What is Retrieval-Augmented Generation? Now we're doing this because we know that we have RAG documents. So yeah, we're being very, very direct here. But in a real world scenario, you want to provide as much documents as would cover the amount of areas that you want your users to query. So these are the two that we set. Is going to assume the model name and the model provider to be Hugging Face because we're going with default for now. So let us hit enter and see what we get. Hopefully no errors. This is supposed to be faster because we already have all our stuff processed. So in no time we should have our results returned back. Okay, yeah, we have them. They're coming all chunked. So if I go up, the very first result, see top documents, the very first result is coming from the Weaviate MD file. That is the website blog. And it says Retrieval-Augmented Generation. This page introduces you to Retrieval-Augmented Generation using Weaviate, and gives us, this is just like the beginning of the blog. But we're also showing just 500 characters, so that's there. The second is also gotten from the Weaviate blog, as you can see with the .md file. This is the file part, and it says why use RAG? Why use RAG? LLMs are powerful, incredible, but can suffer from two important limitations. They can confidently produce incorrect or outdated information, also called hallucination. So you see, we're getting results back that tallies, and you can see they are being cut off, not because of the chunk. Right now, it's just because we're just displaying 500 characters out of each. But if you look at them fully, you also see that they actually have a break-off point. Then this one comes from the PDF. This third result comes from the PDF. And as you can see, there's still a bit of struggle with PDF, the processing of PDF. You can see some breaks here and all that. But yeah, some results says during the fine-tuning process, the model weights of the pre-trained LLM refers to the weight model are iteratively updated through a process called backpropagation. This is just talking about, let's see if we actually captured anything. Okay, yeah, it mentions RAG here. It says such as specificity, style, or tone. RAG enhances generative models by enabling them to reference external data, improving and a cost of here. Because we're just showing 500 characters basically. So yeah, this is more like a comparison between, I think it's a comparison between fine-tuning and RAG. Yeah. Then from the book again, it talks about context enhancement. It's particularly useful when data needs to be preprocessed. Let's see where it mentions RAG. Let's see, window retrieval. There's something about retrieval here and all that. Now, you see, we're getting results. And definitely the results have to do with RAG. But sometimes you might want to question the quality of the results. You think you might get better results and all that. And that is where RAG optimization processes come in. Chunking strategies, like I mentioned, chunking strategies. For example, if we look at the Weaviate docs, we can see some chunking strategies there. Let's go. Yeah, see chunking strategies. We have fixed size chunking. Can I bring this up? Yeah. Okay, good. As you can see, fixed size chunking, recursive chunking, document-based chunking, semantic chunking, and there are even some strategies for even query transformation. You can take the user's query and rewrite it. It's also some of the things I mentioned in my cheat sheet. Query routing, there's hybrid search, which is where you combine semantic and keyword search. And that's vector search and keyword search. And yeah, re-ranking, yeah. So you can also re-rank your results. Sometimes what is returned is not really showing the order of relevance to the query. So you can do some re-rankings. You can even use an LLM to help you re-rank your results. So there's a lot of ways you can optimize your RAG process. This is RAG raw. And you can see it. You can see the power. You can also see its flaws. So you kind of get the idea of why it's a whole industry on its own. But yeah, we've seen RAG in action. Let me clear this. Let's see if we can try our OpenAI model. I'm going to delete my Chroma store. This is actually a process you might need to automate so that when you want to run your build once again, you just automatically delete existing assets. So this time, let us try and rerun the build step and provide more options. So let's say after the chunk overlap, we want to provide, what other argument is that? Okay, I need to go to main. So we want to provide model name, or let's just say, let's provide embeddings. Let's just provide embeddings provider. I think that should be enough. We'll use the default model that we specified. So say embedding provider, set that to OpenAI. Do I need to set that as a string? Let me just say that as a string. So OpenAI. Embeddings provider, OpenAI. Let's see if we don't run into any errors. Yeah, let's hit enter here. So as you can see, we've also been able to chunk, and it also produced 59 chunks. It also produced 59 chunks. But this time we're using OpenAI. We're using OpenAI this time. And if we run our query, let's run our query once again. And this time let us provide our embeddings provider. How do we provide our embeddings provider when we are querying? I think it's also embeddings provider. So query, this time would do this. We'll say embeddings provider equals OpenAI. So let's search and see what we get. Okay, I doubt if there's going to be any big difference, but let's just go up. Some difference though. So the first result from OpenAI came from the RAG docs, which is the .mv file. That's the blog from the website. It also starts from the beginning where it starts talking about RAG and all that. The second one came from the book. If you remember when we used Hugging Face, the second one also came from the blog, but the second one came from the book. OpenAI is kind of, I don't know, just doing some funny stuff with the way it's processing the text here. But yeah, got some stuff that looks a bit unreadable, but yeah, a guide on different techniques to improve the performance of your Retrieval-Augmented Generation applications, post-retrieval, indexing, and stuff like that. Let's look at what's okay. So he got the third results actually from the blog, the same why use RAG section, and then the final result is from the PDF. It says during the fine-tuning process, the model weights of the pretend LLM are basically the same thing that was also done by the Hugging Face model. So yeah, that is how you chunk. You can try out Google. You can also try out different models. Like we just specified OpenAI, so we use the default OpenAI model. I think that should be in like pipeline. That should be in pipeline.py. Where's get embeddings? It's get embeddings. Yeah. So as we specified OpenAI, it basically used this model, but we can still specify a different model, a different embedding model for OpenAI, and it will use that exactly. But here we've been able to see how RAG works. We've been able to build an entire RAG pipeline from scratch, something that you can improve on, something that you can move into production, and you can use it to augment the responses that are generated from your LLM, which is the main purpose of RAG. So Remember, if you want to learn more about RAG, check out my cheat sheet. It's basically your pocket guide for RAG. But for this series, this is all we'll be doing for now. Like I said, if you want me to add S3 support, where you can just throw in an S3 URL and you can dump your files there and your RAG pipeline will automatically pull files from there, let me know. Also, let me know if you want to see me automate this entire thing with ZenML.